In July 2026, the European Union's Right to Repair Directive takes full effect. For manufacturers of in-scope products, this enforces a strict legal obligation. Repair manuals can no longer remain internal secrets. They become public documents. To understand how this legislation works in practice, we have to look at the baseline for quantifying a product's lifespan. We look to the French Repairability Index. If we map this index on a balance scale, a loophole appears. Technical documentation is worth the exact same 20 points as physical ease of disassembly. An awkward layout can recover a fifth of its score just by publishing a detailed PDF. The layout doesn't move, the number does. Manufacturers have reacted exactly how you would expect, by treating this mandate as a documentation compliance exercise. They are reviewing product paperwork and launching free access web pages, but none of this requires a single physical design change. Writing a better guide for a broken layout doesn't fix the underlying hardware. The manual itself is merely the symptom of a failed physical design. To get past the paperwork, we have to look at the physical friction of a repair. The Senelec standard, EN 45554, approaches this by measuring disassembly depth, literally counting the number of steps required to remove a part without causing damage. We see this friction in this timeline chart tracking the iFixit scoring methodology. iFixit traces the full repair path, applying a time penalty at these data spikes every time a technician swaps a tool. This quantifies exactly how often a person must stop, reassess, and reach for something else. But while metrics like disassembly depth and tool swaps accurately measure physical friction, they leave a massive blind spot. They miss the psychological friction of whether a person meeting a model for the first time can figure out what to do just by looking at it. Hardware engineers rely on access topology, that is, the strict physical order in which parts must come off a device, fixed completely by the internal layout. But topology is not repair legibility. Legibility asks whether that required access sequence is actually inferable by the user. Look at these two layouts. On the right, the groupings and shapes naturally guide UI to the first step. On the left, it's a visual guessing game. True legibility is made up of unglamorous, specific details. It starts with whether the fastener heads are left visible in plain sight, or intentionally buried underneath a cosmetic branding badge. It extends to component variation. If the screws holding the outer housing differ completely in size and type from the screws anchoring the logic board, a technician cannot accidentally drive a long screw into a short standoff and destroy the motherboard. On a macro level, legibility relies on grouping components by subsystem. The overall shape of the internals should immediately telegraph exactly where the battery is located without needing a map. A product can possess a theoretically flawless access topology, yet remain entirely visually opaque. The problem is, those two distinct failures register identically on a compliance scorecard. To fix legibility, we have to trace the timeline backward. We have to move off the factory floor, past the tooling stage, all the way back into the concept room, where the layout is born. Early in that phase, layout decisions are fiercely optimized by teams focused entirely on volume, thermal paths, manufacturing cost, and line time. Repairability is rarely the priority. It is not that repair legibility actively loses the argument in that room. It is that nobody makes the argument at all. Design teams need a smaller, harder reframe. Stop viewing your repair manual as a post-purchase deliverable. You have to read it as a harsh public critique of your early layout choices. Look at this blueprint layout. If step 1 requires a complex callout box just to locate the first fastener, you aren't fixing a documentation gap. You're exposing a permanent design flaw. By the time you realize the mistake, the components are locked in place and cannot be moved. That is the harsh reality of hardware design. Once the architecture freezes, you cannot fix the layout. Your only remaining option is to write a better manual to mask the friction. This is why tools from Depix exist, because design decisions are cheap as a sketch, but brutal once tooled. You need to see every angle before you build.